Okay, we are recording. Yes. Do we have any questions? I hope you all are studying, and as I told you, having no questions means either you understand everything or you do not understand anything at all. So it could be either ways. So I hope it's the first one. And because so far, I mean, things have been very easy, not that difficult or challenging, but still, if there's anything that is not clear, please make sure you ask me now, because next week you will be having your first quiz, okay? And based on how you perform, I can actually assess and get a hold of the level of the class, okay? So please ask me questions if you have to, and stop me if you need to ask me anything while I'm talking. Interrupt me, it's okay, all right? So if there's nothing, I can continue. So let's recap what we have studied last time. Last time we talked about graphical methods, and I introduced one of the graphical methods, which is the method of bisection, if you remember. In the method of bisection, which was this guy, the main thing that you have to keep in mind is that you have to only look at the sign. Let me use my pen. The sign of the two initial points that are given to you, A and B. So basically you need 2 points, A and B. You find the functional value of those points, and the product should be negative. That means they should have opposite signs. So that's the one requirement for bisection method. And also we said that if you want to terminate, or you decide when you decide to stop, either when the midpoint that you obtain every time is the functional value of that is equal to 0. That means close to the root, or the difference between the functional value of A and B is less than some epsilon value. Okay. And I'm sorry, the difference between either the functional value or the value of A and B itself, it doesn't matter. Okay. The difference between them, well, I would say A and B because it depends on the function. So if your function is like great, it has a bigger curve, then it would actually be different. So if you say the difference between A and B is less than some epsilon value, that's when you know you have to stop. So epsilon, you can take it to be like 0.001 or some very small value, okay? So as I said, it requires 2 endpoints, A and B, and this method always guarantees convergence. That means always finds the root as long as we know that the function, the f of x function, actually cuts or intercepts the x-axis, okay? If it doesn't do so, bisection will not work over there. Okay, the good thing about this method is that it's easy to implement, but it slowly converges towards the root. That means every time it divides into half. So we have other methods which actually converge faster. Okay. Then we talked about another method, the Newton method. This is a very widely used method, and it is not bracketing method. It is what we call an open method. Now, what's the difference between a bracketing method and open method? The previous method was, well, actually, yeah, the previous method was a bracketing method. That means you had a bracket, A and B, and you had to find the root within that bracket, okay, some point within that bracket. The open method is actually a method that is based on a formula. And that formula either requires a single starting point, okay, as we see in Newton's method, or the open method would be based on a formula that requires 2 starting points, but these 2 starting points do not necessarily have to bracket the root, okay? It could be any point such that the root is not between those 2 points. It can be anywhere on that function, okay? So this is known as open method, and basically the Newton method that we saw last time is an open method. And it uses a function, as I said, and the formula over here is the function, the first derivative. So this is the formula. So we have to calculate the first derivative in Newton's method, okay? So it requires you to calculate the first derivative, and using that first derivative, you have this formula, which is over here. So basically, what does it say? So if the red line over here is our function, we have a starting point, say x naught. We find the functional value of x naught, take the slope at that point, which will be the tangent, and see where it cuts the x-axis, okay? And then that point will be our new point, which is x1. Then you do the same. So basically you find x1 by plugging in the value for x, which is x0 in here, and f of x0 and f of x0, the first derivative of function at x0. Okay, so with this function, you get the next point x1. Then again, instead of now we put x1 on the right hand side, we find the derivative functional value, which is this point. So the tangent will be this point. So this is x2, and you find where x2 actually intercepts. You find where this green line intercepts the x-axis. That would be x2. Then find the functional value and keep doing that until the difference between every two consecutive points becomes less than some epsilon value, or the point that you get, that means the functional value of that new point is equal to 0. And it's equal to 0, that means it's a root, you stop. If not, if it's a very small value, you are good enough, you can say it's approximately close to the root, and so we can stop. Okay. So the good thing about this is faster than the bisection method, because at every time it divides the interval, or it divides the search space quadratically. Okay, but it has some drawbacks, and one of the drawbacks is basically it requires derivation of the function. So if a function is a polynomial function, we all know how to take the derivative, but if it's something more complicated and weird, then finding the derivative may not be that straightforward, and evaluating it also may be difficult. So that's why it can be challenging depending on what function you are looking at. Okay, so let's look at the conditions or the situations in which this Newton method would actually not work as we expect. Okay. So this is one of them that I talked about last time. So I was able to find some graphical representation, because last time I drew it in MS Paint, which was not quite impressive. So I decided to find actually a nice plot, and this is what I found. So for example, one of the drawbacks of, well, it's also called Newton-Raphson's method. Okay, so if you search the internet for Newton method, there are several Newton methods, so don't be confused. This method that we are talking about is Newton-Raphson's method. Okay. So what happens? So basically, this is the root of the blue line. Okay, this point over here. So what happens if there is an inflection point very close to the root? Okay, so for example, if I choose x naught over here, okay, and at this point, okay, I take the functional value, okay, draw the tangent, you see I get x1, okay, and then again over here, basically Newton method should be taking me towards this point, so I should be getting closer to this point, but as you see, if I take the functional value and tangent, I'm moving away from this point as compared to x naught, x1, x2, okay? So again, if at x2 you take, it will go somewhere very far away, so it diverges from the root, okay? And this is because if there's a point of inflection, which is very close to the root, all right? Another situation is that when there is something called an oscillation around the local minimum or maximum. Over here, we have a local minimum. So assume that I start at this point, okay? So we want to find the root, okay? And as I said, that a root over here, it depends, you start with a single point. So over here, and in Newton's method, you need not, it is not needed for the function to actually cross the x-axis, okay? It can solve it even if the function doesn't intercept the x-axis. So if this is x naught, all right, and basically if you draw the tangent at this point, it would take you to some point like x1. And then at x1, you take the functional value to draw the tangent, takes you x2, x3, x4, and it keeps so at x4 you see, when as a slope, as you get closer over here, the slope is getting farther away from the point, okay? So that means you're diverging away from the point, okay? So this is another point, another condition, that is when point that you choose is close to some local maxima or minimum point, okay? Then you have what is called an oscillation. Okay, this is interesting. If you have this kind of curvy function, okay, so assume that you have x naught, okay, and x naught basically is close to this root, right? So this would be the root that you expect to find, okay? And what happens is actually, if you do that, so if you have such a function with such a shape, when you have x naught taking the functional value and the derivative would give you x1, and you see that over here, instead of getting closer to this guy, you are getting away from this guy. So the tangent at this point would be taking you somewhere else. So probably it will lead you to some other point, some other zero value, but not the value that you were intending to go. Okay, so this is another case. So if you have an area of interest and you choose x naught such a way that you want to get close to this point or this point, you see that if depending on the shape of the function, it may actually take you away from your point of interest. This case is if you have a zero lope, okay, this is a disaster, because if you look at Newton's method, which is over here, we have the derivative in the denominator of the function. So what happens if the derivative is zero? It would give you division by zero, right? Which is something that is not good. If you're writing your code and you get a division by zero, you know what happens. So basically, if, for example, you have x0 over here, it takes you to x1, and at x1, when you draw the slope, it will be flat, 0. Okay, and at this point, since you're finding the you want to find the next point, so you have to put f prime x is equal to 0 in the denominator. It will give you division by 0. Okay, so it basically doesn't hit the x-axis, it just shoots off. Okay. So these are some of the cases that exist, or some of the cases in which the Newton's method wouldn't function, okay, or work as we expect. Any questions so far?
No, I believe.
No? Okay, then I have a question for you guys. Okay, let me see. I have written a question for you to solve. Okay, suppose you have a function f of x. I want you guys to write it down because this is not in your slides. I guess it's not in your slides. E to the power minus x. So I want you to use Newton's method to estimate the root of this function. And the initial guessing point would be x naught is equal to 0. Okay, so basically what are the steps? Can you tell me in Newton's method? What would be the steps? What would be the first thing you would do?
Find first derivative.
Speak out loudly so we all can hear. Loudly, please. Derivative. Yes, you find the derivative. Thank you. First thing you do is step number 1. You first find the derivative of fx. What's the derivative of this function? Let me ask. Wait, no one tells me. I want to ask someone. I want to see if people are there. Aidos, are you here?
Yes, I'm here.
Okay, what's the derivative of this function, sir?
The derivative of this function is minus e to the power of minus x, and that's all.
That's
minus
all?
1.
Oh.
No. And
oh, you scared me. Yes. Okay, so this is the derivative of that function. So now if you remember, what's its name? If you remember where is that equation? The equation. So now we found the derivative. You plug in the derivative at x is equal to 0. You have the value of x is equal to 0. X is equal to 0. You find the next point, which would be x1, right? Is it clear? So basically now what you do is you evaluated this step 2. What you would do is you would evaluate the derivative of x at the point x naught, which is equal to 0, right? And then you plug it into the Newton's equation. And when you put n is equal to 0, you solve and you find the next value, which is x1. And you keep doing this until either you get to the root, or either when the difference between the two consecutive points is less than some epsilon value. Is it clear? So this is something you guys keep in mind and try to solve it. Just wanted to give you a heads up. Okay, where are we? Where is this? Why are we here? Oh, we're far. What happened? Bisection, Newton's. Okay, secant method. Okay. Now let's look at another method, which is the secant method. And this is another method, which is an open method, okay? Now, as I told you, what's the problem with the Newton's method? The problem is that it may become a potential problem when you want to implement the Newton's method if you have to evaluate the derivative, right? So evaluation of the derivative is where the challenge is. As I told you, if it's a polynomial or many other easier functions, then it wouldn't be much difficult. But if it is some function which is very inconvenient to evaluate, then that's where the challenge lies, okay? So what we can do is, instead of actually finding the derivative, how about we approximate the derivative with some difference function, okay? So this can be done. Let me bring my pen again. So, okay, in secant method, it's also known as linear interpolation method, okay? So it's a different name for secant method. And I told you why we have, what is the strength of secant method with respect to the Newton method, because Newton method or any other method that requires a derivation of a function, it may not always be easy. So that's why we need to somehow replace or approximate the derivative of a function with some straight line, okay? Now, a straight line, to get a straight line, what you need is you need 2 points, right? So basically it's an open method, it starts with 2 points. And I told you that open methods can have either one starting point, okay, or it has 2 starting points, but it is not necessary for the root to lie between these 2 points. Okay, keep that in mind, very important. So in what we want to do is, now we want to approximate the slope f prime x that we had in Newton's method with a line. We can do that if we have 2 points. So assume our 2 points are x0 and x1. We have the functional values at these 2 points, fx0 and fx1. So the approximation, or the line approximation, would be this function, which is also known as the forward difference. What is it? Forward infinite divided difference. It's the name of this function. If you search the internet, you will find it. So there are different functions. You can have f of xn approximated to f of xn minus 1 minus f of xn, okay? Or you can have positive. So basically, if you have a line and you have some point xn over here, you can have x of n minus 1 here. Okay, I'm sorry about that. And this is xn plus 1. So you can approximate this line by taking the point which is before x of n, or you can take the point after x of n. So this guy takes the point after after n. Okay, so the derivative at the point xn would be equal to the functional value of some point x of n plus 1. That means which is after the xn. That means that means x of n plus 1 is greater than x of n. Okay, keep that in mind. Minus this divided by the difference of the 2 points. Okay, so this function over here is sorry. So this function over here is the function that will be used to approximate or to replace the derivative function that we had in Newton's method. So if you do that, you basically see that this is what you would get if you replace it in this place. So if you replace this guy, this denominator, with this function, okay, and you rearrange the equation, this is what you would get. You would get your next point in terms of the previous 2 points. Okay, so we have 2 points, which would be these 2 points, x0 and x1, and we want to get the next point, which is x2. So what you do is, instead of the derivative function, you just replace this line function, which is an approximate function, and you just do the same as in Newton's method. As long as the difference between the 2 points is less than some epsilon, or the functional value at this new point is equal to 0, that's when you stop. Okay. So basically, this is this is how it looks. So if the red line is your function, you have 2 points over here. I have I, okay, and let's say this is a -1, okay. So what I do is I draw the line passing through these points, and I find the point at which it cuts the x-axis. So at this point, y is equal to 0. So I get a new point, and then I take these 2 points, that means this point and this point. Okay, so basically this would be some point here. And then I try to draw a line between these 2 points to get close to the root. This will be my x next point. Okay, let's call it x prime. And then again, I take these 2 points and I draw the line that is going to that, and then that will take me towards the root, which is over here. Okay. But also in this case, secant method looks beautiful, right? But it has so it kind of what we say converges to the root quadratically. That means it's fast, it's good, as against the bisection method. But the problem with it is it has the danger of extrapolation. What is extrapolation? Is that, for example, if I start with x0 and x1, if I choose these 2 points as my starting points, and I draw the line that passes through the functional points, their functional values, I would get x2. Now I have to take the next 2. That means x1 and x2, draw the line, and I get x3. Okay, then I get x3 and x2, which is here, and I draw the line. This is this point, and as you see, this has a danger of extrapolation. That means it will never get close to the root. Okay, okay, so this is what I said. Instead of using the derivative function, it uses a difference function, which is easy to compute. So it has a problem extrapolation. That means it may diverge from the root, but other than that, it is faster, or it's easier to use compared to Newton's method, because you do not have to calculate the derivative of the function. You replace it with an approximated line function. But again, since it's an approximated line function, it has a problem of extrapolation. Okay. Okay. So yes, sir.
How close should x n plus 1 should be compared to x n?
Okay, good question.
There is no rule.
So basically, what you're asking me, how do I choose these 2 points? Okay, how do I know what 2 points to choose in order to converge towards the root? Is that what I'm understanding?
Yes.
Yes. Okay, good question. So in our next lecture, we will be studying about methods or elimination methods of actually how to find this bracket. Okay, because we are talking about 2 points. Let's start with some 2 points, but these 2 points can be anywhere along the x-axis, and it could have any functional value, and God knows whether how it's going to behave. So there should be some way to actually find some what we call smart starting points. Okay. So how do we do that? We will do that in our next lecture. But for now, let's assume that we know where these points are. Okay, so there are another bunch of algorithms which help us find the starting points. Okay, and once we have the starting point, then it will be easier to implement these methods. Okay.
Okay, thank you.
Great. Good. Any questions? Okay. Let me see. So this was the secant method. Okay, so okay, in bracketing method, as I told you, what we do is in bracketing method, the what is that? The root should be between the 2 starting points. But in secant method, we saw that it doesn't have to be the case. We can have the root to be anywhere else and 2 starting points to be anywhere else. Okay, so that's why it is not classified as a bracketing method. It's an open method. Okay. Now, our next method that we will be seeing today is the regular falsy method. Regular falsy method, actually, I wanted to show you guys something, but I will keep it for later on if we have time in the end. Okay. Let me see, where is regular falsy? Because I'm looking through 2 different sources to try to, cover as much possible or give you as much material as possible regarding each method. Okay, regular falsy method. The regular falsy method is also known as false position method. Okay, if you Google and you find this name, it's the same. Okay, and it is a bracketing method. Okay, keep that in mind. And basically, it tries to combine both the bisection method and the secant method that we just saw. Okay, so what was the problem with the bisection method? The bisection method, the problem was it was slow, correct? I mean, it would divide it into half every time, but unlike bisection method, secant method was fast, quadratic, okay? So this is plus, I'm sorry, this had 1 plus and this is 1 minus. Now, what is the minus point in secant method? It had the danger of extrapolation. But in bisection, we say that what we say, the function crosses the x-axis, then there is no extrapolation. It guarantees convergence towards the root. Okay, so this is the plus point of this. So now what this guy does, it takes this plus point and this plus point and comes up with a new method. We have something in the chat. Yes, you can use spline method for interpolation, Daniel. Good question. But what is spline method? That is out of the scope of this course. I will not be covering that. But I mean, there is a course on numerical methods, which you guys should have had in your second year, or I think the new curriculum, I don't know, one of the curriculums has it in the second year. And they teach, actually, I taught this course like once. There we cover spline method. Yes, sir. We can use it for interpolation, but that's not what we'll be covering today. Okay, Dania? Okay.
Okay, thank you.
Removes the danger. Okay, what was, okay, so now this regular falsy guy, he takes the plus point of this and the plus feature of this, and he tries to come up with a method that combines these two, okay? And so basically, what you do over here is you find, so there are 5 steps to it, okay? And you basically, since it's a bracketing method, you will have to have 2 points and the product of their signs should be opposite, okay? So this is the condition of bracketing methods. First thing, you find the slope at some point B, a functional value of B, then find the slope at B, okay? And you can find it because you have 2 points. So what you do is the delta Y divided by delta X, okay? Then step 2, you find the line that is passing through these functional values, f of A and f of B. And that we just saw how to do it. You have this equation over here, okay? Then when you put y is equal to 0, you find the x-intercept, okay? So in this line equation, if y is equal to 0, you'll find the point at which this line crosses the x-axis, so you would get this, okay? And what you do is, now if the functional value of this c is equal to 0, or the difference between b and a is less than some epsilon 0, that means you have found the root or you're close to the root, so good enough, you stop. If not, then you take this f of c as your new point, replace it in place of b. And if this is the case, then this is what you do. If this is not the case, that is greater than 0, then you, instead of replacing b, you replace a with c. And then you repeat doing that again. So you go back to step number 1, okay? So if you want to, in other words, I'm sorry about this overlap, but okay, so in other words, if I want to tell you, so we know what similar triangles are. So for example, if this is your function, the blue line, okay, and you're given 2 points, x of L and x of U. This is A and B, similar, taken from a different reference. So if this is x of L, x of U, and the point at which it intercepts the y-axis is x of R, so you see we have 2 triangles, the smaller triangle over here and this bigger shaded triangle over there. By the rule of similar triangles, what we say that we can say that this x point, okay, the intersection point, or what we say that these 2 triangles, or the slope, okay, is equal. That means delta y by delta x is equal to the delta y by delta x of the 2 triangles, which is this equation. Am I right? Because this line will be basically passing through these 2 points. So over here, when we have x of R, which is the point at which it crosses the x-axis, so what you do is you factor out xr and everything else on the right, and this is what you would get. Okay, so basically, this is the same equation as the C equation, which I've written over here. Okay, so this is how you come up with this. And so how do we now know which of these 2 points, xl or xu, this xr should represent depending on the sign? Okay, so it replaces that point which has the same sign as xr. So xr over here is negative. So basically xl will be replaced by xr, then your next 2 points will be xr and xu. Okay, and you repeat the same thing again. Is it clear? Guys,
Yes.
Any
Can you please
questions?
Go back to the. Yes, I have a question.
yes, sir.
Can you please go back to the previous slide?
Yes, sir.
Here in step 2.
Let me clear out
uh,
everything so that we can see. Yes, sir.
In step 2, is it a mistake? C minus B. Should we use C or X?
Well, I'm not talking
It's
about
just a
points. So
notation.
basically, these are just points. A, B, C. Since we are using the notation A and B, I'm just using C. I'm sorry,
C
I didn't get
is-
you.
C is a variable or a constant?
C
Yeah, it's a
is
variable.
Because
it's a point.
in step 2, we don't have C yet. We find intercept in the next step.
no. This guy is a equation of a line, right?
Y of X,
Yes.
Y of C. Yeah.
Y of C.
Yes, this is a well. Yes,
Ah,
I mean,
okay.
come on.
I
Y
understood.
C in terms of C. Okay. So actually, C is the point X. So if you take X, if you can replace it with X, and afterwards you write X is equal to blah blah blah.
Okay.
It's just a matter of notation. I'm sorry about that.
Sorry.
Is it clear, or should I explain?
No, it's clear. I thought C is a constant.
No, it's not a constant
I
here.
didn't-
It's not a constant. It's a variable. Just to be consistent with A and B, I have written C. Sorry. Yeah.
Thank you.
Good.
Yes, it's
Any
clear.
questions?
Thank you. I have no question.
Anyone else? Good. So now we saw 4 methods, and this is how. So in terms of convergence rate, so this is important. I have summarized something that probably you'd have to read a lot in order to get to this conclusion. So I've done it where. So this slide is very important, actually. It took a lot of effort to come up with this, so I've made your life easier. So in terms of convergence rate, so if I want to tell you, okay, which one is faster, okay, which one would converge faster towards the root of the function? Well, it depends, again, as one of our friends asked, the starting point that we have, okay? So if we begin with a very good starting point, okay, or points, what happens is Newton's method would outperform the other guys. So Newton's method would be better. Then we have secant method. Newton method better because we are using the actual derivative, okay? Secant method is less better than Newton because we are approximating the derivative. So it's obvious. And since the open methods of quadratic in terms of running, in terms of convergence, so they are better than the bracketing methods, which are regular, falsy, and bisection, okay? But if you do not have a good starting point or interval, then obviously these two may fail. But this two will always converge because we always know that in this bisection method, the 2 points that are given, or the regular falsy method, the 2 points that are given will always include or will always bound the root. That means it is the lower upper bound of the root. So the root is some point between them. So it will always converge, okay? So basically, this is how we can summarize the 4 methods. So do we have any questions regarding the 4 methods?
Yes.
Yes, sir.
Why the regular falsy method is faster than bisection? Or
Regular
both of
falsy
them
is
like n squared.
Regular falsy is faster than bisection because in bisection, if you remember, we had 2 points, and every time we took the middle point. So if this was my XU and XL are my 2 points, if I take this as my middle point, you see this would be my XR. But regular falsy takes the point at which the line connecting XU and XL intercepts X. So you would get this point as your XR, okay? Now, in this case, if you look, now, okay, this was step 1, okay? So let me go back and show you why. So in bisection, what I would do is I would find the midpoint, which is XR, okay? Then I know that my root is not in this upper half, so I look at the bottom half. So again, I would divide this into half, say some point here. Again, I know my root is here, so I would again divide into here. So it will take me longer time to get to the root, right? But in the regular falsy method, what it does, it draws the line between the 2 points, takes that point at which X is intercepted, takes that as our XR. Okay, now if this is my XR, So now this line and this. So this point and this point. So you go here and this, and then you connect these 2 points. And if you do that, you would see that this would actually, well, in this particular case, maybe we don't see the convergence, but if we have case in general, if you can say, depending on general functions, or if you look at all the set of functions, it has been shown that it converges faster. That means it doesn't divide into half. It takes more than, it eliminates more than half of the search space in every iteration. Okay, am I able to explain it?
Thank you.
So in every iteration, the regular falsy, like the other methods, as I told you, regular falsy tries to take the plus points of secant and the bisection. Okay, so the secant thing was, the good thing about secant is that it was quadratic. That means in every iteration, in finding the new point, it removes more than half of the search space. So it reduces the search space quadratically, not by half, not logarithmically. Okay. But bisection does it logarithmically. So so if you compare the search space in each iteration, you would see that the secant method, I'm sorry, the regular falsy or the secant method, they give you a smaller search space in each iteration, which is easier, which tells you that, okay, you don't have to search the whole building, you only have to search the 5th floor, right? Yes. Hello. Can you hear me, guys?
Yes, we can hear. But
Please, someone please let me know,
yeah.
because I feel like when I don't get response, I feel like I'm talking to myself, and that's not a good sign. People will think I'm crazy. Okay, so did I answer your question, young man?
Yes, yes.
Good. Okay, now let's look at okay, this is why, okay, good. See, I wish you would have asked for something else. See, I have an example over here, which tells you, okay, using bisection method and regular falsy method, okay, I've given you a function, and I've given you 2 starting points because that's a bracketing method, so you need 2 points. So your points are 0 and 1.3, and I say, okay, implement both of them, which will basically be one of your assignments, because you will have to do implementation in this course. So implement bisection method, implement regular falsy, and you tell me which one converges towards the root. So can you tell me what is the root of this function? I want you guys to solve and tell me.
1.
1?
Yeah.
And -1.
And -1.
No, I mean, this is a bracketing method. So obviously the root should be between 0 and 1.3. So is it 1?
Yeah.
Is there anyone who has a different root than 1? No, good. Okay, so if you use bisection method, okay, so I said bisection method, it converges slowly, okay? So as you see, it is going, okay, and it's getting close to 1. Is it clear? Do you see that? In each iteration, it goes down, it gets closer to 1, right? And over here, what we see is for the regular falsy method, okay? In the regular falsy method, we see that it is going down, it is converging, but it's going very slow. That means at the 5th iteration, okay, we have already reached the root in the bisection, but over here, we haven't reached yet. Why is that? As I told you, in general, regular falsy is better than bisection, except for some cases, and this is one of those exceptional cases. Look at the function's behavior. Look at the behavior of the function. This black line is my function. So if I use regular falsy, I'm taking a point, okay, 2 points, obviously, this point, this black point here, and this black point here, okay? And every time I'm drawing the line, connecting them, and this will be my new point. And again, I take the line connecting. So as you see, bisection method would converge faster because every time divides into half. But over here, it's not dividing into half because of the behavior or because of the curve of your function. Is it clear? So every time you see the search space is reducing by this much, this much, this much. So it's going towards the point that we want, but it's going very slowly. It's not growing it's not decreasing quadratically. But in general, it does so. Okay. So basically what we could have done is, instead of taking the because in bracketing method, our condition was that the 2 points should have opposite signs. So what happens if actually I take some sign over here? So if I would assume that it doesn't have that condition is not necessary, we would see that actually if I connect this point and this point, so some line would take me closer to the point. And then if I draw that functional value and I connect these 2 points, it would take me closer to the root. Okay. So again, there is a condition. Every method has some condition, but depending on the function that we are trying to solve or find, solve, it depends on how. So the thing that you have to take home is that you should always check your results by substituting the estimate that you get for the root in the actual equation. Okay, so if you get some value, always put it back in the equation and you see whether it's closer to 0 or not. And also, it's always good to do this test with using more than one approach. Okay, so as we know, Newton's approach is good if we have good starting points. So first we have to learn how to get a good starting point. If we know how to do that, then Newton's method is the best. Okay, if we do not know how to do that, then regular falsy and bisection would always work. So use this. Okay, so this is when you, so in the exam or quiz, if I ask you, okay, use elimination method to find the starting points and then solve this function f of x, blah, blah, blah. So when I say use elimination method, that means I'm asking you to find a smart starting point. And if you do that, then what I want you to do is basically just use Newton method after that, because you know the best starting point and you know Newton's method would be the best, would give you the best convergence, would do it faster for you. Okay. But if I say, okay, choose any points you want and solve, find the root of this function, then in that case, you would say, okay, there's no elimination. We do not have smart starting points. So let's use either regular, falsy, or bisection. Хорошо? Good.
Yes.
Good. Do we have any questions?
Not yet.
Not yet. Good. Okay. Unimodality. I'm thinking of whether to continue or stop. Let me introduce what unimodality is, and then we will stop. Okay. So basically, up till now, what we have seen is we have this problem, optimization problem, which is minimize some function. Okay, it could be maximize function. It doesn't matter. As I said, maximize would be minus of f of x. Okay. Now, if we want, and there is no constraints, just minimization, simple unconstrained optimization problem. So we have to find some value of x that minimizes f of x. Now, if this function f of x is differentiable, that means we can find the derivative. What we do is we use the root finding problems that we have seen so far, right? It would be a root finding problem and we can solve it graphically as we have seen. But if it is not differentiable, then what you have to do is you have to evaluate that function. So you have to plug in the value into the function, find the functional value. Okay, so there is no root finding in that case. So as I told you, depending on whether the function is differentiable or not, there are two approaches towards finding the minimum of a function. Now, let us try to concentrate on a particular type of function, okay, which we call unimodal functions. Now we call a function f of x to be unimodal in some given interval a and b, including a and b, okay, if there exists some unique point x star within this interval, okay, and two other points x1 and x2 within this interval, such that the value of x1 is less than x2. So we have x1, we have this x-axis, okay, we have some interval a and b, and we have 3 points, x star, x1, x2, and x1 is always less than x2. This is one case and this is the other case. Okay, is it clear? And so x star can be anywhere within this interval. Now, listen carefully. If x2 is less than that x star, or if x star is greater than x2, okay, let's see. In this case, x star is greater than x2. Then, if the function is unimodal, I'll tell you what unimodal means. The functional value of x1 will always be greater than the function value of x2. So keep in mind, I'm comparing x2 with x star, but then I'm comparing the functional values of these two guys. Similarly, if x1 is greater than the x star, as in this case, so x1 is after x star, then the functional value of x1 would be less than the function value of x2. So using this x star, what I'm telling you is that a function is said to be unimodal if there exists only one local minimum or maximum within that loop, within that interval. So that's basically what this definition is saying. So from now on, we will try to focus on functions that have only a single minimum point between some interval a and b. So we do not consider functions which are like, I don't know, this. So this has multiple points, right? Minimum points. So we only consider those functions within a given interval such that within that interval, there's only one minimum value for that function. So we define that as a unimodal function, and that is done by using these points x star, x1, and x2. So basically, x star is the minimum for the function f of x within the interval a, b. Okay, and obviously, since it's the only minimum value, it's known as a strong minimum, right? Clear?
Yes.
Okay, so when so if I'm telling you, so if I say that f is a unimodal function, and there are two interior points, okay, within the interval a and b. So I'm saying that within the interval a and b, I'm giving you 2 points x1 and x2, okay, and the function f is unimodal, and obviously x1 is less than x2, okay. Then now, if see, the reason why I'm defining unimodal, because we are going to use this to find the elimination method. And what is elimination method? Elimination method is finding, or is a method that we use to find the smart starting points that we talked about. Okay, so given x1 and x2 within an interval a, b, and f is a unimodal function, if f of x1 is greater than f of x2, okay, then we can say confidently that the minimum point, the local, the strict minimum point is within the interval x1 and b. So let's look at this. If functional value of x1 is greater than functional value of x2, then the minimum point is between x1 and b. So the minimum point would be between x1 and b. So it will not be over here. So you can remove this part. Okay, so you reduce the search space to here. Is it clear? If f of x1 is less than or equal to f of x2, if f of x1 is less than or equal to f of x2, as in this case, okay, then the minimum point will be between a and x2. It will be between a and x2. So we can remove this point. So this is known as the elimination step. So what we are trying to do is we're trying to find some point, okay, such that so we are trying to find a point which compared to the other points has a lower functional value. Okay, so now let's define the elimination step. Choose 2 points. So that's what you guys will do. You're given a function, choose 2 points, x1 and x2. Okay, and so within some interval a and b. Okay, so I'll give you an interval, say from 1 to 5, and so you choose any 2 random points within that interval such that x1 should always be less than x2. Find the functional values at that point. If the functional value at x1 is greater than x2, then your new interval would be starting from x1, okay, to b, and if it is less than or equal to 0, then your new interval would be from a to x2. Okay, and you keep doing this until this condition holds. Once this is violated, that means you can stop. That means you have found that point x star, or your interval a and b has become so small that it encloses that x star very closely to it in it. Okay, now how do you find this? We use these 2 methods. So there are 2 methods: the Fibonacci search and golden section search. We'll be talking about next. How to find or choose these 2 interior points. Okay, any questions so far? We will do, these are just examples for this lecture, so I recommend you guys to go through these examples. Okay, so what we have talked about today, I have solved it using finding the necessary and sufficient condition. If you see F prime and F double prime, I've given you an exercise to do. Then for using bisection method, I have solved over here and I've shown you how to choose bisection. And again, I've given you an exercise to do using bisection. Then again, over here, I've given you an even function. You know what even function, whether it's f of, you know what even function is, guys? F of minus x is equal to f of x. So basically it's a symmetric function where whatever value of x is, positive or negative, it will always be symmetric. It's as shown over here. And then I use Newton's method to solve it. And then I ask you to solve these two equations using Newton's method. And this is another exercise using secant method, and 3 exercises for you. So please work out these things, okay? I've given you one example and I've given you some exercises. So you know this is regular falsy method. And I've written the code for this. So I want you guys to also be able to write the code and get the similar. So basically to know whether you've done the right thing or not, you have coded it properly or not, do repeat, write your code, do it for this function that I've already solved, see if you get the same values. If yes, then whatever other exercises are there, it should probably work correctly. Okay, if you have any questions, always email me and we can work. I can look into your code and help you if you find your mistake. Okay, guys. So basically that's it for today. You will be having a quiz next week. Now, whether it will be on Tuesday or Thursday, that is something that you should be prepared for. Okay, I will not tell you the date, but it will be next week. Okay. So prepare, and the coverage would be till the end of what we studied today. So the end of unimodality, okay, would be covered in your quiz. So the end of what lecture is it, 2 or 3? We are in lecture number, let me stop sharing and let me see. This is lecture number 2. Okay, so lecture 1 and 2 in your first quiz, study well. And basically the quiz will be as such. The quiz will be available on Moodle at exactly 12 noon. What you guys would have to do is I will have a Zoom session and I'll be online. If you have any questions regarding the quiz, if you do not understand something, you can always join the session and ask me. But then other than that, you have to just download the question from Moodle. You have to solve it manually with your hand. Okay, write it down as if you're writing your exam. Once you're done, you'll have to scan it. So there are a number of softwares. Ainur, please, you can contact your TA and she'll tell you the software. There are some apps which you can install and it can actually take picture of your solutions with your cell phones. And you upload those solutions to Moodle, okay, within the deadline. So probably you will have like, I don't know, how much, 1 hour, 15 minutes to do everything, to solve and scan, okay? And then you upload it to Moodle and that's how I will evaluate it, okay? Is it clear?
Yes.
Yes.
Okay, so please make sure that you have your software, you have everything prepared, you have your A4 papers, your pen, pencil, whatever ready. And make sure that I am very well aware, or it's very easy for me to find out your group chats and all that stuff, okay? I can do that very easily. I did it in my previous sessions, and those students who were caught, they got a 0, and I did not report them to the school. But if it repeats this semester, I'm going to do it, okay? So make sure that you do not cheat. This is an individual effort. You do not have to cheat, because if you study well, there's nothing very complicated about what you have studied so far. Make sure you study well, do it yourself. It's very easy for me to identify whether it is a copied solution or not, because one single mistake or one single line or something which is very similar is very easy to catch for me, okay? So if one person makes a mistake and it is repeated in many solutions, that means it tells me all of you guys have copied, okay? So please, I'm requesting you guys, do not do it. Do not make me have a bad impression about you guys. I do not want to do that. I know you guys can do it. The quiz is not that difficult. You can do it. Time is enough. Just do your best and let's see how it goes from there, okay? Well, if there are no questions, we can end the session for today. Questions?
Sorry, Professor, I have
Yes,
a question. Can we use software like MATLAB for our assignment, because there's some 3D plot, or should we draw it by hand?
3D, I won't give you a 3D plot. I'll basically just give you a 2D. For your assignments, I will definitely ask you to write code in MATLAB or in Python, and that's where you'll have to prepare a report, and you'll have to show me your code as well as your plots. So that will keep it for the assignment. For your quiz, drawing by hand is more than enough. You do not have to have any software. But please have your MATLAB or anything installed for your assignments, which will be later on. Or actually, you have an assignment, I believe. Yes, you have an assignment. In your assignment, you can use software, but you have to include your code. I need to see the code that you've written, whether it's your code or you have taken it from somewhere. Хорошо?
Okay, thank you.
You're welcome.
Хорошо.
Thank you.
Okay, guys.
Okay,
Thank you.
thank you.
Thank you, guys. Take care of yourselves. See you day after tomorrow. Bye-bye.
Bye.
Goodbye.